All right, I'll go ahead and start then.
Gente, tem mais comida que eu esqueci de colocar na mesa.
So, hello everybody. My name is Daniel Grimmer. I think there's no one new in the group. So just for context, I was a former PhD student at Eduardo's group at the University of Waterloo. And then recently I graduated last year and came to the University of Oxford to study physics, or sorry, to study philosophy of physics. And so I'm doing a master's here, and I've just applied to do a second PhD, a DPhil here. And this project I'm going to be talking about was actually my research proposal for that. So I think there's a lot of content here. I think it's going to be good to think about and talk about for the next couple of years at least. So let's just jump into it. Okay, so here is an outline of the talk. I'm going to be talking about something which I've come up with, which I think it's okay to call discrete general covariance. And I'm sort of motivating why this term applies to whatever I'm going to talk about. So there's three parts to the talk. Part one, we're going to review some philosophy of GR, which I've learned recently. So what is special about general relativity? Is it something called general covariance? Is it something called Diffeomorphism invariance? Is it background independence? Those are three interrelated concepts, which I'll hopefully try and clarify a little bit. And then we'll need to talk about the Nyquist-Shannon sampling theorem for a while to get that under our belts as well. And then putting those two together, I'll motivate what I'm going to call discrete general covariance. Right? And this 20 should be up there, but whatever. Okay, so after each of these three parts of the talk, I'll pause for questions. And if you could just please save any major questions for the period between the parts. If you have any clarifying questions, please bring them up, but save any major comments till then. All right. So some philosophy of GR, just to set the background. So what is special about general relativity as opposed to special relativistic theories? In some sense, we have a feeling that there was some big breakthrough that Einstein had, some conceptual breakthrough. And we look at the history, and it's unclear exactly what that was as GR developed. One thing that Einstein definitely thought was very important was general covariance, which is the fact that our laws should not change their form depending on the coordinate systems that we go in. And a generally covariant theory has that property, that it has the same form in all coordinate systems. And certainly general relativity was the first theory that had this historically. So maybe it's that. Maybe it's the fact that GR is Diffeomorphism invariance. Again, general relativity was the first theory in history that had this sort of thing, where its symmetry group was the full diffeomorphism group of the manifold. Or maybe it's the GR's background independent, which means that roughly it has no fixed background structure. And again, this was the first theory in history to do this, but is that really what makes GR new? Is that what sets it apart from all other previous theories?
Sorry, clarifying question then, clarifying question. So did you say what's general about GR, right, and special? Sorry.
Right. GR is the most special of all the relativities, I like to say. So, okay, so how do these three concepts differ, and how do they relate to each other? There's a lot of muck around these three concepts, which I think we should get straight. Because what I'm going to do is I'm going to propose something, a discrete version of just this first one, just general covariance. So first I'll talk about what these three are. And a spoiler for part one, the answer to that question, what's special about GR, is its background independence. And this is the consensus of the philosophers that I've been talking to here at Oxford. And I think it's generally the consensus outside of that as well. But general covariance is not a special property of general relativity. It was pointed out by Kretschmann early in the history of general relativity that any theory can be made generally covariant. Right? But nonetheless, general covariance is an important thing to think about because it exposes background structure. Once you separate out the coordinates from your theory, it becomes very clear what you're talking about in your theory and what your theory asks you to believe in. And it also helps clarify a lot of questions about symmetry when you write things in a generally covariant way. So this is a very good thing to do, even if it's not exactly what makes general relativity special.
Dan,
yeah?
just a stupid question. Is that Kretschmann the same as the Kretschmann invariant, that guy?
I think so.
It has to be. The dates check out.
It might be. This is 1917. The history lines up.
Because I'm not sure if Kretschmann scalar was invented by then, but yeah, maybe it's the same person. Okay.
I don't know. And sometimes things are named posthumously for people, so
yeah.
It could be. Okay, was it option B? No. Diffeomorphism invariance is not a special property of GR. In fact, I'll show you later how special relativity can be written in a diffeomorphism invariant way. But again, it's important to think about diffeomorphism invariance because it's a necessary condition for background independence. Anything which breaks your diffeomorphism invariant or breaks the diffeomorphism symmetry of the manifold will end up counting as background structure. It's sort of the fixed background structure which doesn't vary with the symmetries.
So Dan, one thing that you wrote here that confuses me is that the group of symmetries of special relativity is more like something like SO plus 1,3. And SO plus 1,3 is nothing like Diffem. So I'm not sure what you mean by this. The group of symmetries are different.
No, I'll show you later. I do this explicitly. I can write special relativity in a way that's diffeomorphism invariant.
All right.
You'll be surprised by it when it comes up.
No, but diffeomorphism invariant is just like changing coordinates, right? I mean, you can always change coordinates, right?
We'll get to this. We'll get to this. Okay. I promise all that will be answered. This is the spoiler. So we'll get through all this.
Looking forward to understanding that statement better.
We can argue about this at the end of part 1. Okay. So it turns out to be background independence is what makes GR special. Is what I'm going to try and argue in the first part. But really, I guess the first part's not necessarily to convince you that it's background independence. It's just to get you clear on what these 3 concepts are and how they differ. Okay, so let's work through a first example about general covariance. So here I've written down the equations for the 2D Klein-Gordon equation. The time derivative equals the spatial derivatives minus the mass term. And we can take this to be a real field. Let's just imagine it to be real. This formulation is not generally covariant because if we switch coordinates and write the same equation here in terms of these new coordinates t prime, x prime, which has this like acceleration term, and y prime, then you'll find that this is the equation that the field obeys in that frame or in these coordinates. So the form of the equation has changed and it's not generally covariant. So when you move to arbitrary coordinates, you find extra terms due to non-inertial frames.
So then, sorry, but the way that I approach this, at least like the way that I think of these things, is that essentially what we do is that we add another term to take under consideration this change of coordinates. So for instance, if you write the 2D Klein-Gordon equation in terms of the Christoffel symbols and the connection itself, right? Then, I mean, you're also going to get an extra term that will somehow be canceled by this thing that is enforcing this that is canceling out these extra terms, right? Is that a fine way to think of this?
Yeah, I think that's a fine way to think of it. I think you're just playing with what derivative you're using, actually. But if you have a mathematical object which obeys equation 1 in these coordinates, then it obeys equation 2 in these other coordinates. It's pretty easy with calculus to show that. But let me get on to the next slide. I think this is probably what you're saying. So if you write down the Klein-Gordon equation in terms of in this different form, and then you do it just an arbitrary change of coordinates to some other coordinates x prime mu, it turns out the field in these new coordinates obeys this equation. So you have the metric here undergoing 2 change of basis transformations, right? And then you have these connection terms sort of showing up, these second derivative things. Right. So, and you can modify your derivatives to cancel off these terms. And that's basically what we do in the next slide. So what's best to do is just to get away from coordinates altogether and to write your theory in the coordinate independent language of differential geometry. Okay, and the way that the philosophers I've been talking to like to do this is and I know other people do this too, but I've first come to really study it here. So we think about the space of all kinematically possible models for our theory, which is basically just the set of all of the mathematical objects we need to make statements in our theory, whether or not they're true or false, or whether or not the dynamics is satisfied or not. So here, in this case, we'll have M be a 2+1 manifold. Eta is a fixed metric with some signature -1, 1, 1, and phi here is a real scalar field defined on the manifold. Right, so once you have these objects stated, you can then pick out which of these models are dynamically possible, this is the space of DPMs, and they also obey this additional equation here, that in fact they obey the Klein-Gordon equation. Now this nabla A here is the unique derivative that's compatible with the metric here that has this. Right, and so once you've written your Klein-Gordon equation in this generally covariant form, now you're no longer referencing coordinates in any way. And when you do a change of coordinates, nothing really changes in these. And I should mention, by the way, that normally when people write one of these tensors with some indices on it, they're thinking about the components of the tensor in a particular basis, or in a particular set of coordinates, or a coordinate basis, whichever. You can also just think of these as the abstract objects themselves. Like, we'll come to that. Maybe I'll say that again on the next slide.
Yeah, but this one, this index thing, you are essentially saying you, instead of the usual Einstein notation, you are saying this is like the Penrose abstract index, right?
I think that is. I think that's the same thing. I'm not quite sure on the terminology, but yeah.
Yeah, Penrose abstract index notation is saying that AB is an index that tells you what tensor it is. It is not a component, and then you use mu to denote the components instead.
Exactly. Yeah. Okay, that is exactly what I'm talking about then. Right. Okay. These indices, don't think of them as labeling the components of the thing in a certain coordinate. These just tell me what rank the tensor is in which ways and how it interacts with the other ones. So I don't mean to say that these are the components in any given coordinates.
So there are three conventions that are common. Yeah. The Penrose one is the least common among physicists usually, which is well understood. There's another one. So this could be confusing depending on the audience you talk to, Dan, because good that you clarify this, because the usual, maybe it's a good idea to have a slide when you talk to other audiences and explain the different conventions.
Right, I had considered that. I thought it was an important point to.
Because usually like Roman A, B, C, D is also used commonly. That's what I take, for example, in my year course to express components in an arbitrary basis, then Greek ones in a coordinate basis in particular. You see, the distinction between coordinate basis versus arbitrary basis is also used often. It's a common notation to use Latin characters A, B, C, D versus mu, rho, and so on in differential geometry. So those are different conventions, and it's good that you explain it and saying that these are not components. It's just not. It's like having a tool, saying the type of the tensor. That's kind of the only thing.
Right. Yeah. I just mean to indicate by them the type of the tensor and how it contracts with everything else. Right. So I don't secretly have coordinates going on in the background. These are really abstract objects.
And also it's important to say that you don't need to refer things to bases, because not all bases are coordinate bases. And that's kind of interesting because that's also why people use this other notation too. So if I were to write this like this, I could say, oh, this is in an arbitrary basis rather than in a coordinate basis. See what I mean?
Right.
And that's the ABC. Right. So it's good to say that you are writing things coordinate independent. This is the tensor itself, not expressing coordinate independent, sorry, basis you're not expressing any basis, coordinate or not.
Yeah, okay. I did mean this. Yeah, go ahead.
At any rate, what equation 7's notation is using is basically what Walt is using. So yeah.
Yeah, that's correct. That's the Walt notation. Yeah.
Right. Okay. Right. So we talked about how we can write the Klein-Gordon equation in this generally covariant way. I'm going to call this whole theory SR1, and SR2 will be something else that'll come up. But anyway, so eta AB here is a fixed element of here. It doesn't obey any dynamics. It's just stated at the level of KPMs. We just fix a particular tensor field there, which acts as our metric. And the fact that this is fixed across all the solutions here qualifies it as background structure, and it breaks the diffeomorphism invariance of the manifold. So what I mean by that is if you're given a generic diffeomorphism and some solution to this Klein-Gordon equation in 2D, then if you act the pullback or the push forward, whichever one's appropriate, on your objects, if you do that to both the metric and the field, it's not going to be a solution in general. And if you apply it just to the field, it's not going to be a solution in general also. So this thing doesn't have a full diffeomorphism symmetry, at least not the way I've written it now. I can rewrite it later, so it does, but we'll get to that. And so in particular, like only the Poincare symmetry group the subset of this will have these be solutions. Okay, let's repeat this process for the heat equation, just to show sort of how it works in a more general setting. So here we have the heat equation, which says that the time derivative of some heat field psi here is proportional to the second derivative of the field. Okay. And so here you again get a space of KPMs, which picks out a bunch of like geometric objects we need for our theory. And there's a lot of them. I'll just quickly run through them. It's not important to remember what all these are exactly. But to write this down in a generally covariant way, you need a space metric HAB and a time metric TAB with signatures 0, 1, 1 and 1, 0, 0, respectively. You also need to pick out a derivative operator, which is compatible with these in the sense that the derivatives of the metric is 0. And also you have to specify that it's flat. Just specifying that these that it's compatible with these metrics isn't enough to specify the derivative operator. We also pick out that it's flat, and then that makes it unique. And then TA here is a constant unit time-like vector field. And time-like meaning that its contraction with A, with H is 0, and its contraction with T is 1, right? And this picks out a standardized way of moving forward in time. It's the translation generated by the contraction of this with the derivative. Anyway, so that's just a bunch of geometry you need in the background. And then the dynamical equations then for this theory are picked out by the derivative of the field in this T direction is equal to the contraction of two derivatives with the metric applied to the field. So this is the generally covariant formulation of the heat equation. So you can really do this for any equation.
Then how does the time metric show up in this equation 9 there?
The time metric doesn't show up explicitly in 9. The time metric is needed to normalize TA.
Oh, I see. Okay, thank you.
Right. So it's TA has all these objects here. There's a bunch of equations that relate them to each other. The derivative acting on the metrics has to be 0, and the derivative has to be flat. And so TA contracted with capital T contracted with lowercase t twice has to be 1, and capital T contracted with H has to be 0, which just means that it's that's what it means to be a unit time-like vector field in this setting. All right, so yeah, but you're right that lowercase t doesn't appear explicitly in 9. Right. Okay, and just one more example of a generally covariant formulation of something is you can do the same thing with Newtonian gravity. You have a metric, you have a manifold, your two metrics, a derivative, and you'll have a gravitational potential and some capital phi, which is a stand-in for the matter content of the theory. And somehow rho, the matter density, is calculated from that. And then you have the Poisson equation here, and then you have the geodesic equation here, which just says that that the acceleration of a particle, of its forward velocity is normalized. Is just given by the gradient of the potential. Is
this Newton-Cartan?
No, this is not.
Okay, so what's the difference with Newton-Cartan?
In this, yeah, that's a very good question. In this one, we are taking this derivative here to be a flat one as well. The same condition here is flat. Now, it turns out that if I don't pick out that the metric is flat, it turns out there's a lot of different derivatives which are compatible with these metrics. Like in Lorentzian theories, your derivative is uniquely defined as the one which is compatible with the metric, right? Yes. But in this case, it's not that. And so there's some freedom. If we drop that flatness condition, there's some freedom in which of these derivatives we pick. So it turns out that there's a derivative which sort of absorbs this term.
So you're not so hold on here. So it's when the connection that is compatible with the metric uniquely defines a connection. The condition of if you have no torsion, the condition of making the covariant derivative of the affine connection compatible with the metric fixes it 1-to-1. There's no degeneracy.
The metrics here are degenerate. They've got
they're degenerate. Okay, no, that explains it. Yes, right. Yes, of course. Yes, yes.
So yeah, in the Newton-Cartan theory, you do this same sort of thing, except you drop the flatness condition and you pick a derivative which sort of cancels off this term.
Yeah, I see.
So that you have things following geodesics with no force then in a curved spacetime.
Gotcha. So
And
that's
you
the
can do-
equivalent, the demanding of the in a way the equivalence principle in a way. The fact that gravity is geometric, right? The Newton cartan demands that gravity is geometric, whereas this doesn't.
Right. Yeah. So you can geometrize gravity. But I haven't done that here, but you can, and that's
Perfect.
the key conceptual step from Newton gravity to Newton cartan.
Gotcha.
That's a very good question. Right. So I just wanted to show this as another example of this. And in this case, there's no time-like vector TA assumed here. So the heat equation, I had to pick out a standard way of moving forward in time, right? But here I don't. These equations don't involve that. And this theory has the Galilean symmetry group.
Then I just want to clarify what Eduardo just said. So
Yep.
by not geometrizing gravity, which is not Newton cartan, right? You are saying that in this dynamically possible model and the kinematically possible model, right, you don't have a Riemann curvature tensor.
Right. I'm using the same. The Riemann tensor is fixed to vanish.
Right. While
It's
in
part of our condition for defining the derivative.
Right.
This vanishes.
Right. While in the Newton cartan, the R, A, B, C, D should have components which corresponds to the second derivatives of the gravitational potential.
I think it turns out something like that.
And you would get a geodesic equation with a zero in there to reabsorb the terms.
Yes. Okay, I see. Basically, you require that. It's a weird thing where the gravity is like a field on top of a flat space-time, I guess.
That's right.
Yeah.
Right. The gravity is given by Okay. Let's see. Right. So this has the Galilean symmetry group. All right. So I've shown you so far that we can write lots of different theories in a generally covariant way. So that's definitely not so special about general relativity. But we probably should write most of our theories in a generally covariant way, at least if we want to be very clear about what is going on inside of them. So writing a theory in this coordinate independent way, what it does is it separates the theory's substantive content from its superficial coordinate dependent properties. Like if you want to be realist about your theories, which means that you want to believe that everything you talk about in your theory, like there's a corresponding element of reality that is that thing, then you're going to end up basically believing in all of the things which are talked about in your angle brackets here. Like you have to believe that all this structure exists. This is a great way of finding out what those sort of substantial content of your theory is. Right. And since any theory can be represented in terms of any coordinates or in terms of no coordinates at all, it should now be pretty obvious that coordinates play no role in symmetry. Like if you really want to understand what the symmetries of a theory is, I think coordinates are only confusing. And in particular, in a coordinate independent framing of a theory, there are no more passive symmetry transformations. All symmetry transformations are active because they actually move the fields around on the manifold. And any passive transformation is just a change of coordinates, and those are all either trivial or you can't even make sense of them. And so the symmetries of a theory are just the subset of the diffeomorphisms which map solutions to solutions. Or at least that's the space-time symmetries of a theory. There are non-space-time symmetries also. Okay. So if it's not general covariance that makes gravity special or GR special, let's say maybe it's diffeomorphism invariance that sets it apart from special relativity. Right. Well, this is not right, sort of unfortunately. You can reformulate special relativity to be diffeomorphism invariant in this way. So here's a theory called SR2, which is just the same as that special relativity I talked about before, the Klein-Gordon equation, right? And the KPMs here are a manifold and a metric here, and this metric is not fixed. And we have, so it's not fixed at this level, it's fixed later on dynamically down here. And we have models, and we have a field phi here. And so we obey the Klein-Gordon equation with respect to this metric. And we also obey separately that the derivative is flat, or sorry, that the metric is flat. Right? So it turns out that in this theory, if you're given a diffeomorphism, a general element of the diffeomorphism group, and some solution to this, then if you transform all of the objects according to this diffeomorphism, then it is still a solution. And so this is a way you can write special relativity in a diffeomorphism invariant way.
But it feels a bit cheating though, because this group of diffeomorphism is not the group of diffeomorphisms of GR. It's a different group of diffeomorphisms. You have changed the differentiable
manifold. This is the diffeomorphism group of the manifold. I'm not sure what you said.
What is the manifold? Yeah, what is the manifold for you? Is space-time? Is the space-time manifold?
Yeah, it could be. Well, you're going to have issues like, okay. When you fix this R condition, R equals to 0, I think it places some like topological restrictions on which manifold you're allowed.
Right. Yeah. I feel as if the M is a different thing in GR than in this theory.
Right.
These are diffeomorphisms.
Right. So I think in this theory, the manifolds you can think about are restricted, but it is still the full diffeomorphism group of whatever manifold it is.
Yeah, but that's something there's a lot of generality in that. I can write many theories as diffeomorphism invariance in some manifold, right? So playing with how you restrict the manifold, definitely you get different symmetry groups out of the group of diffeomorphisms, right? I mean, I don't know by heart, but if I restrict to a sphere, for example, the group of diffeomorphisms in a sphere is not the group of symmetries of GR. And yet, it is a group of diffeomorphisms.
If the manifold that GR is on is a sphere, then it is. But
there's no GR on a sphere.
No.
Well, yeah. But this is a Lorentzian manifold, and this is a Lorentzian metric.
Sorry.
It's not something that.
Because there's no Lorentzian metric for a sphere. but yeah. Erickson, you would say something too.
No, I think maybe the idea is that diffeomorphism group, right, doesn't need metric, right?
Right.
So that means you can change whether you have a metric or not, right? You can still change to exactly the same coordinate. If I do GR, right, I put a metric on it, I can do the same diffeomorphism as someone else who didn't do GR but use the same underlying differentiable manifold.
Yes.
So I can change coordinates however I want, regardless of the curvature tensor, right?
Yes, that's obviously correct. Yeah.
So in that sense, there is no need for restriction because two people can use the same differentiable manifold, but you can argue that one of them is a Lorentzian manifold while the other one is just a smooth one.
So diffeomorphisms are defined. You can define a group of diffeomorphisms the moment that you have a Lie derivative.
Yeah, exactly, which means that you don't need to do any restriction on the manifold, right? Essentially, diffeomorphism only cares about the underlying smooth manifold, not the matrix structure.
Well, what we're saying is the manifold is restricted by this flatness condition in this case. You can't. There's some manifolds which you can't put a flat metric on them, I think. Right.
Jose also wants to say something, I think.
No, I was only going to say that you said that to define the group of diffeomorphisms, you need the Lie derivative or something.
Yes.
I don't think so. I mean,
no, you don't.
But you don't. But okay. But you need smooth maps on the manifold. That's what you need. Yeah, diffeomorphism smooth maps.
Not even a smooth map. So you only need a. No, you only need.
You don't need smooth maps. You only need
a C1. Well, not even C1, just a differential manifold. And considering the differential maps that are differentiable in both sense, that's the group of diffeomorphisms. You can define it just in terms of differential.
They need to. So the group of diffeomorphisms is invertible bijections that are smooth, from the manifold to the manifold.
Not necessarily smooth.
How smooth is smooth?
Okay.
I mean, it depends on how much smoothness you want.
Yeah, okay. It depends on your on whatever you want. Yeah, sure.
Yeah, and also it's the transition functions that need to be smooth, not the.
No, that's a different thing. Forget transition functions. You don't need coordinates or anything like that for this. Just a map that goes from the manifold to the manifold that is smooth, and then a map. Of course, to call it smooth, you need to talk about the coordinates. What they do when you map to Rn, not coordinates.
You don't need to talk about particular coordinates. You need to talk about an atlas.
That's right.
You can take the maximal atlas, which is like the union of all compatible atlases, and then you obviously not talking about particular coordinates. So anyway, yeah, this is a bit of a trick. It is a bit of a trick, but you can write special relativity in a way where its symmetry group is something much larger than the Poincare group. Right? And now the solutions to SR2 are one-to-one with solutions or equivalence classes. Let me say it this way. Up to diffeomorphism, the metric here is the same metric as SR1.
Yeah.
Right. So there's what you've done is you've just taken every metric in SR1 and then just widened it. And then you move wherever you want in that equivalence class sort of to compensate for the changes you made to the function here. Right? If that makes sense.
But doesn't it mean that you're expanding the theory, though? You're including extra symmetries that are not justified from an empirical principle in special relativity, right? The only symmetry that you're justified from experiment, from first principle in special relativity is the Poincaré group, right? Not the
right. Yeah. Well, you're right that it may be hard to motivate this formulation of SR from, but this formulation of special relativity makes it easier to make a transition to general relativity. Let me show you this on the next slide.
I think
like you have your special relativity 1, and then you can do a rewrite in terms of special relativity 2, and now this is closer to general relativity. Like the only difference between this and general relativity is that you don't fix the metric to be flat, you instead fix it to be coupled to matter by Einstein's equation. But the space of kinematically possible models here is the same in GR and this, right? You're just changing one of the dynamical equations. So that's the only difference between this theory and general relativity.
So it's a Hamiltonian curve. So you're saying that the GR, so special relativity is the same kinematical space. This SR2 has the same kinematical space as GR, and it's just a constraint that fixes that you're in special relativity 2 versus a different constraint that fixes that you're in GR. Is that
right? Yeah, that's what I'm saying. But I mean, you shouldn't take this kinematically possible models, dynamically possible models. Don't take that too seriously, because I mean, what I just showed is that you can take SR1 and you can like move some bit of structure between them. Like in SR1, we had the metric fixed just by fiat, right? And here we fixed it dynamically, whatever that means. Right, so whether or not you move something from KPMs to DPMs, there's sort of freedom to do that.
It does feel a bit artificial in the building of the theory, though, in the sense that I mean, I think I understand, but it feels a bit artificial, this SR2 theory that you're building.
But it is equivalent to special relativity 1. It's just a reformulation of it.
And then, please, why is the Klein-Gordon equation important at all on this 12 formulation? Could I just write like R equals 0, and that would give an equation of motion, if you will, for this dynamical metric, and that's it? Like, why is the Klein-Gordon field important?
Oh yeah, sure. I just wanted to have some content in the field. But I mean, if there's no matter content, then your theory has no dynamics in SR2. I mean, okay. Right? If you drop the Klein-Gordon equation, this R A B C D equals 0. That fixes the metric up to diffeomorphism in SR2. And so diffeomorphism is just the symmetry of your theory. So you have no dynamics. Like you just move within your symmetry class and you don't.
The way that I see this is that like you have this equation of motion for the metric, which is essentially like a tensor, a real tensor quantity, a tensor equation, right? And that is why you end up getting this diffeomorphism, invariant or general covariant, whatever you want to call this.
Sorry, I lost you for a bit.
Oh, I'm sorry. There was a thunder here, so maybe it's that. Yeah, sorry. Yeah, I'm back. So the thing is, the fact that we have this tensor equation of motion for the metric, that is the thing that sort of gives us a differential. How are you calling this? A general covariant, a different diffeomorphism invariant theory in the end. Is that a correct way of thinking?
Yeah, I think so. I think you're right about that, if I understand you right. But let's move on from this because it's not really what I want to spend all the time talking about. But these are very good questions, and we can talk about them more later. So what makes general relativity special is not exactly diffeomorphism invariance or general covariance. It's some third thing, which the consensus has agreed on a name, background independence for it, at least in the philosophy literature, but not exactly what that is. So let me step back a second. Special relativity 2 here still has background structure, whereas GR doesn't. And that's because this, like I said, this thing is fixed up to diffeomorphism all the time. So it basically counts as background structure. It doesn't really evolve. It's not coupled to the matter. It just, so that counts as background structure anyway. So even when you rewrite special relativity in this way, there's still a substantial difference between it and general relativity in that case. But,
and I'm sorry, it's not very clear to me what you're calling background independence. I'm so sorry. Is it like coupling to matter or not?
Yeah, that's exactly what I'm going to talk about now. So the main debate in the philosophy literature on general relativity at the moment I think, is exactly how to define background independence. There's a lot of different proposals about how to do it. So when I say it's some third thing, let's call it background independence, this is just putting a name on it. Like exactly how it's formalized is still a matter of much debate. But I don't want to get into that here because it's not exactly relevant for the rest of my talk. So again, let's move on to part two. So any big questions about what the difference is between general covariance, diffeomorphism invariance, and background independence are?
I do have questions though. I don't know how long it will take, but I do, because again, this SR2, this way of writing special relativity as a Diffeom-invariant theory, feels to me like special relativity. You add extra symmetries. Certainly you add. It's like if I were to add an extra gauge to my theory that wasn't there justified for first principles that you don't seem to need, just because you want to intellectually justify. I really want to do a Diffeom-invariant theory. What do I need to add to my theory to make it Diffeom-invariant? And I tell, well, you need to add this extra level of symmetry, and this extra level of symmetry has consequences. Now you have a gauge theory. Special relativity wasn't a gauge theory. Well, at least not in the way we think of gauge theories. Now it is. It doesn't feel to me that it's the same theory, even though I understand that you can get the same equations of motion out of it, and you can make the same predictions out of it. It feels like an inflated version of it. I haven't seen the justification other than I really want to write it artificially as a
No, it is an inflation of the theory, and it's not exactly natural to do it this way. And I'm not saying SR2 is the right way to think about special relativity. What I'm saying is, so suppose I'm wandering around in the wild and I find some new theory and I check it out and it has a diffeomorphism symmetry of this kind. But there's a bunch of objects in my theory, and I notice that when I do D star to all of them, it's still a solution, right?
Right.
So I find this theory in the wild and I'm wondering, wait, is this a special relativistic type theory or a general relativistic type theory? If we're forcing to make that distinction, right? Like the fact that you have this, that you notice that there's this transformation property among your solutions for this wild theory you found, it can still be a special relativistic theory.
Yeah, I understand that. But
that's all I'm saying here in terms of, because the question was what makes general relativity special? Like if I come up with some new theory, is this a special relativity type theory or a general relativity type theory? Like you can't use the fact that you have this diffeomorphism transformation to make that distinction.
But there's an argument to be made that if I want to do general relativity, right, what is the smallest symmetry group that I need to consider from first principles to do GR, and that's the group of Diffeomorphisms. But if I ask, what is the smallest symmetry group that I need to consider to begin to build a special relativity theory, the smallest one possible, that is not the Diffeom. That is a smaller group. So in that way, they're different. From first one, how you go from the first principle to the theory, right?
Right. Yeah, that's exactly right. So I think you're right there. But let's go ahead and move on to part two, and I'll
sorry, then I just wanted to have I'm also having a little bit of trouble understanding the difference exactly between the what we call generally covariant theories and diffeomorphism invariant theories. What it sounded to me is that basically you can make any generally covariant theory diffeomorphism invariant by adding an analogous background structures as you did in SR2 there. Is that an accurate description?
I don't know about that. I haven't thought that out. That might be right.
Because
I'll have to think on that. Yeah.
Because what you just described sounds very much like the discussion that people have on covariant phase space, and there they use this confusing vocabulary that calls basically what you're calling background independence, they call general covariance. So, for example, when Wall talks about generally covariant Lagrangian theories, for example, what he actually has in mind is theories with no background structure. So they're basically talking about the same thing.
Right. Yeah. I agree that lots of people use these three terms sort of interchangeably. And I think it's very confusing exactly how people use them. So that's why I wanted to go through this first part and tell you what I mean when I say each of those words. And what the philosophers here at Oxford mean when they say those words. I don't know, I haven't done enough reading to confirm that wider, but but I don't know if you can make any theory diffeomorphism invariant by reformulating it, by just sort of inflating the symmetries. Maybe you can, I don't know. Okay.
And then the final question I will have with that, but Jose has another question though. Go ahead.
Well, I was going to say some things about what Edu said about the symmetry of a special relativity. Well, I think it was already clarified because I think that the thing of formulating it this way is like, I mean, you're just considering any symmetries of the flat metric, and in particular the condition on the metric, like, in fact, characterizes all the metrics that are isometric in the manifold that you're working on with the natural flat metric. No, I guess. Well, but anyway, no, I was going to say about on one hand that yes, as Bruno said, I've heard general covariance as background independence. In fact, Luis Garay in his notes, he describes general covariance as background independence. And I also I was going to ask you about the statement you said that special relativity is background dependent. Mm-hmm. You said that because you have this condition of the Riemann, but I mean I would need you to define what are you going to consider a background structure in order to make that statement, right? Because
absolutely, you're right that I haven't spelled that out, and but much of the philosophical literature that I've been reading about this stuff is exactly that. We have some intuitive sense that special relativity has some background structure and general relativity doesn't. But what exactly you mean by that? I haven't spelled that out.
The point is
and that's the big puzzle, is how exactly to do that in a way that's completely satisfying.
The point is that I think that's going to be relative to whatever you are considering. I mean, yeah, it seems that special relativity clearly has some background things there if you examine it from the point of view of general relativity. But I mean, in the end, you are always going to have some background structure. I mean, you have to work with something, and maybe you can always make things I don't know, emptier, or to say something. I don't know. Well, anyway, what I was trying to say is that I think you can, in fact, instead of that you can make anything generally covariant, I think you can always make anything background independent, because it depends on what you define to be fundamental in the general setup that you are applying to your theory. Right?
In that sense, I would say that covariant phase space at least has one answer to what is a background structure. I don't know if that's a satisfactory one, but it at least has one. Namely, it's anything that doesn't vary when you define a variational principle. So anything that's not a dynamical field, a variational principle, is a background structure. So that gives a precise notion also as to what is a symmetry, a dynamical symmetry, and what is not. Because whereas diffeomorphism is not going to act in whatever tensor fields you have, the variations that act on solutions to the equations of motion act only on the dynamical fields. And if you have,
but how does that apply to this equation?
I can. Well, let me jump in here for a sec. This thing about background structure is what's not varied according to like Hamilton's principle. That's something that the philosophers have tried, but people pointed out holes in it pretty quickly. I can write special relativity in a way where everything in the Lagrangian is varied. And you just do that by like adding on a Lagrange multiplier term that fixes this to be 0. And then you just have some funny field which interacts with nothing else, which just moves around just so that it fixes that, right? And so just the fact.
Well, but the point is that that's not adding any real degrees of freedom.
Right.
That's just writing Lagrange multipliers. That's like.
Yeah. No, you're right. You're right. And so there was a second paper responding to the one I'm thinking of that was like, oh, well, that's just cheating. Like you of course you can introduce extra structure and then make it not interact with anything to make it. But so but then how exactly do you write that down? Background independence is when you have a theory and everything in its Lagrangian is varied, and everything in its Lagrangian like corresponds to a physical field or something, or like some dynamically accessible field. Maybe you can get away with it like that, but then you have to clarify what exactly you mean.
So one last comment along the lines of what everybody is saying here. I can move from background independent to background dependent theories in a whim if I want. I can just set the dynamics as Lagrangian, as Hamiltonian, as Lagrangian constraints even. And then suddenly I'm not in a background independent case. You see, it's kind of a choice. That's why it bothers me a lot, because you can formulate everything as background independent or not by adding the dynamics as a Lagrange, as a constraint on your phase space, or just letting it happen out of Hamilton's equation. You see, that's kind of a choice. I don't know what the difference is physically.
No, I'm not taking that to be the definition of background independence.
Okay.
Like we're thinking about what the right definition of background independence should be, and you're right that you can switch between these different types of theories, and we'd like whatever we end up saying background independence to be, to like cleanly cut all the things we think of as having background structure on one side and all the things we don't think on the other. And it's very hard to make that distinction. There's lots of exceptions.
Yeah.
But my talk's not about background independence, but I'd be happy to talk more about it later. Let me tell you what. Well,
yeah, just before you move on, it's not a question. It's actually I have to tell you guys, I gotta leave to the airport like right now in 5 minutes or so. So I have to actually start recording this. Would anyone else be willing to take this burden of recording this and then sending it to me so that we can either put it on YouTube or something?
Well, I can record it.
Oh, thank you so much, Bruno. Thank you so much. That would be great, because I'm really interested in the background, in this whole like discrete part of the talk.
Right.
Dan,
So you're gonna stop recording? And...
Can you make Bruno a co-host now? Nice.
So Bruno, you're recording now? Yes?
Yes.
All right, thank you so much. I'll reach you later to get file Bruno or something like. We'll find some way. Okay, thank you guys, and I'm sorry I gotta leave now, but yeah.
Dan,
yeah, goodbye.
Dan, I just have a yes/no question.
Yes.
So in your dynamically possible models, right? What if, let's say, I conformally couple like the field to gravity? That means I have a conformal coupling. There's a Riemann tensor in the Klein coordinate equation. Does this change the theory into something else?
I'm not sure. I think it would, but I'm not exactly sure.
Okay, that's fine.